Hello, and welcome to Lecture 33 in this Introduction to Proof series based on a general introduction to the art of mathematics. We're going to be going through section 6.5 in the GIM book today, which is about functions. So the plan is, first we're going to sort of monkey around and figure out what is the correct definition for a function. It's a little weird because it's something I imagine everybody feels like they already know, but getting it just right is important for us being able to do proofs concerning functions. Then we'll talk about some properties that a function may or may not have, and finally get down to a specific type of function that are known as bijections, which are very important in in a lot of areas of math, but in particular when we're about to study the idea of cardinalities of sets, and basically learning to deal with the infinite in sets. So let's go. What is a function? We're going to be playing around with this a lot, and this is probably uh, this is probably what I learned as a kid anyway, and maybe what many people have internalized as the definition. We use this term well-defined to say that a function basically doesn't goof around. If you give it an input, it produces exactly one output. A function is a well-defined rule that given any input value, x produces a unique output value, f of x. That notation, f of x, goes back to Leonard Euler, so we call it Euler notation. So if I refer to Euler notation now, that's the kind of grown-up way of talking about the y equals f of x stuff. Here's a more modern definition, but it's not the official definition as we understand it now. And the point is to take functions back to be relations that have a particular property. Okay, so a function is a binary relation which does not contain distinct pairs having the same initial element. That gets at that uniqueness concept, right? That if you did have two distinct pairs having the same initial element, that would be saying the same x went to two different y's. So not so cool. To sort out what's missing from that last version, we need to talk about four sets that are present when we're dealing with a relation. So remember, you're generally talking about a relation. Well, actually, for quite a while now, we've been talking about relations on a set, but now I want to go back to the more general case where a relation is defined to go from a set A to a set B. So it's a subset of A cross B. And I think an example helps to make this clear. Suppose A is 1, 2, 3, 4, and B is do, re, mi, fa. Well, then, maybe I should have said do, re, mi, fa. Anyway, you can think of that as a relation on that is going to, well, actually, a function on those two guys would give you a little four-note melody. So anyway, A cross B contains 16 ordered pairs. That's fairly clear. Right, 4 things in A, 4 things in B. The number of ordered pairs would be 16. You could list them in a big 4x4 table. Here's a particular relation. Excuse me. 1 do is a pair, and 2 re is a pair, and 3 mi is a pair. As I was mentioning before, you could think of that as a song where the first note is do, the second note is re, the third note is mi. Okay, so in this example, there's a total of 4 sets that you can talk about. So first there's the sets A and B themselves. A is the set where you might have left-hand elements in the pairs in R. That's where they could come from. A set where the left-hand elements in the pairs in R could potentially lie. B is the same thing, but for the right-hand elements. So that's where the right-hand parts of the pairs could be. Then I'm calling it A prime and B prime. These two things are the sets of left-hand elements that actually do occur in the pairs in R, and B prime, the same thing for the right-hand elements. So we've got sort of the potentiality and the actuality for both left side and right side in the pairs. Probably true. A picture would help with this, right? So here's a picture for that particular relation, although this is indeed a function. We've got the notes over on this side and the numbers over on the left, and Well, 1, 2, and 3, that's the set of things that actually have a pair associated with them. 4 didn't, right? 4 was not mentioned in the relation. I should go back and look at it. You see how the relation has 1 paired with something, 2 paired with something, 3 paired with something, but not 4. Similarly, the note fa wasn't in there. In fact, I don't know why I backed up, because you can see the relation right here in front of us. 1 is going to do, 2 is going to re, 3 is going to mi. This is the Euler notation for those things in the set. I mean, as a relation, we would just say the pair is 1 do. As a function, and using the Euler notation, we would say that do is equal to f of 1. Anyway, I hope you get the 4 sets. Well, in the definition, in the accepted definition of what a function is, we really don't make this distinction between the stuff on the left. A and A prime are just considered to be the same set. And there's probably, I think there are good reasons for making that choice, but it does give a certain asymmetry to the way we think about things. So again, when we have relations, you can have a different domain than you do from the set that the left-hand elements could come from. But for functions, what we really do is insist that every single value on the input side is defined. That is, there's something that leaves every x going onto the other set. A good way to put it, probably the best way to put it, is that A is literally the domain of f. That there's no A. Normally, the domain of f would be contained in A, and we're going to just insist that it is A. Okay. And it is strange, I guess, that there's no problem with there being a superset-subset relationship on the output side. We can have the range contained in the codomain, but for the left-hand side, the domain just has to be A. Okay, so here's the 3 sets we talk about. The domain of F is the set of left-hand elements that actually occur in the pairs in F. The range, that's the set of right-hand elements that actually occur in the pairs that are in F. And the codomain, well, actually that's just any superset for the range of F. Usually there's some codomain spelled out in advance, but it could be anything that contains the range. So, all right. We're at a point now where we can really say this very precise definition of what a function is. But here's the 2 things in an imprecise way, or sort of to internalize it, to help you think about it. First, a function has to be defined on its entire domain. And second, you have to have a rule that basically gets at the idea of the vertical line test. We'll come back to talking about VLT in a sec. Okay, so here it is. This seems like a lot. If A and B are sets, then F is a function from A to B. And this is kind of important. The symbolic way to say that is F colon A long arrow B. F, and you read that as F goes from A to B. But anyway, that was in parentheses, so that's just a side note. Maybe I should read this without the side note in it. If A and B are sets, then F is a function from A to B if and only if F is a relation from A to B. The domain of F is equal to A, and this is the last bit that incorporates or encapsulates the vertical line test. If you have a pair AB in F, and you have another pair AC in F, well, that implies that B and C are equal. I hope you get that that's becoming a bit of a standard trick we use to kind of make something be true, but when it is true, it's vacuously true. But what's really going to happen if you've got a function, there won't be a pair AB and a pair AC. There will only be a single pair that has A in it. I should reinterpret that using the Euler notation for functions. What was that thing? It said AB is in F. So if I take the line, the pair A comma B is in the function, or is in the relation that the function is, well, that's the same as saying that F of A equals B. Right? A is the input side, B is the output side, and this is what we're more used to. Right? A is the input that gets sent to B by the function. All right, so if I try to say that whole thing, I've got this. F of A equals B. And I've also got that F sends A to C. So that's saying F of A equals C. Those two things together are going to imply that B is equal to C. Sorry, a bit off on there. Yeah, so if you have two distinct things, you think you have two distinct things that are the things that A gets sent to, it turns out you were wrong. They were really equal to each other. That's a way to reinterpret what's written up there, which is what's on the slides here is the statement about the function having the vertical line test property expressed as it being a relation. And what we've just done is expressing that same fact using the Euler notation. Right. So that's the vertical line test. Now, why is that the vertical line test? Remember what the vertical line test does. If you've got a graph, we've got a significant delay in the video for this. Maybe I better do it on Desmos. My video, I'm sort of using a homebrew document camera here that's made by pointing a webcam at a flat surface. And I'll have to restart that. Anyway, here's a function, right? That's y equals x squared. We're all quite familiar with that one. But if I said x equals y squared, Desmos will graph that just fine. And you get something that fails the vertical line test. A vertical line looks like something like x equals a constant. Okay, that's about a different concept. That is very odd. Oh, I see. It's doing y equals. I see. Very strange. If I said x equals 6, would it do that? No. Oh, well, maybe it did, and I just don't know it. Yeah, there's a vertical line. Okay, so let me try to put the graph of the thing that fails the vertical line test back on the screen. It's x equals y to the second. There we go. Now we got them both on at the same time. I don't know what was going on with that. Well, anyway, the point is that a vertical line, that's this green one here, if you move it around, no matter where you move it around to, it hits the graph twice. And what is that doing? Well, that's giving one x value that corresponds to two different y values. So as a relation, no problem, but you guys recognize this is not cool for a function. Okay, so let me return to the slides. Yeah, we spoke about the vertical line test, but basically the vertical line test is getting at this very same property that we've talked about. Well, speaking of properties, that's the next thing to discuss, properties that functions may or may not have. These are things I believe everyone will have run into before, probably in like pre-calculus, if not before that. But, well, A, I want to make sure we're cool on a very precise definition of what these properties mean. And B, I'm going to introduce some sort of more technical language for them. Onto and one-to-one are the things we're talking about. Let's do onto first. Onto means that everything in the codomain is actually in the range. Okay, that is, you map onto the entire set B. The things that are potential right-hand sides actually are right-hand sides. And I don't know if marginally cooler is the right way to say this, but you're talking about F being a surjection. That's a noun form. F is a surjection. That's a type of function or a subcategory of functions that has this property that the range is equal to the codomain. There's an adjectival form of that too. You can say F is a surjective function. I think I put that in here. Yeah. Alternatively, F is surjective. So what does that mean? Well, f is surjective if and only if for every y in the codomain there exists an x in the domain so that that f gets mapped to that y. I think I just said f. That x gets mapped to that y. And the x that must exist gets sent to the y by the function f. Okay. One-to-one, another term that we've heard about before, I think. I personally like to think about one-to-one in terms of what it's not, which is that it's not many-to-one. Many-to-one is when a function maps more than one thing to a particular position, a particular output. Um, so f of x equals x squared, that's usually 2-to-1. Let's bring back the Desmos and do this. I had it all set up before. Y equals x to the second power. Yay. So yeah, this is usually 2-to-1, meaning if you think about a particular output value, say y, well, I'll make it. My Desmos is misbehaving itself lately. I don't know what's up with that. How about if I just say k? And no, it doesn't like that either. Well, I wanted to put a horizontal line on. Maybe I don't need to. Here's a horizontal line. Y equals -2. All right. Um, -2 has two different numbers that get sent. How did I say -2? -2 is down below. It's not there. 2, +2. It's it's got a negative number that goes to it, and it's got a positive number that goes to it. Maybe a poor choice because the numbers are plus square root of 2 and minus square root of 2. I'm not sure if that was smart. Maybe I should have. Oh, I see. Well, if I change the scale, I can get something that has a nice value. 4. 4 has -2 goes to it, but also +2 goes to it. So it's 2-to-1 there. In fact, most places it's 2-to-1. There's one place right at the origin where it's 1-to-1. One input, exactly one input goes to that output of 0. And there's places where it's nothing to 1. There aren't any numbers that give you negative values when you square them, if we're in the reals. Right, so, oh yeah, I made that point. When x equals 0, x and negative x are except when x equals 0, x and negative x are distinct, and both get sent to the same number, whatever x squared is. But of course, when x is 0, x and negative x are the same number, so we don't really have an issue there. Okay, so that means that that function is not one-to-one. One of my favorite functions, one of my favorite examples of a function fails to be one-to-one. But if, for instance, I use g of x as e to the x, that is. Now, oh yeah, the fancier terminology, you can use the word injection. G is an injection, that's the noun form, and the adjectival form is G is injective, or it really is short for G is an injective function. Should we give an example of plotting this e to the x? Now, I suppose everybody knows what that graph looks like. Here's the official definition. F is injective if and only if for every pair of things in the domain, if f sends them to the same place, that is, if f of x1 is equal to f of x2, well, that implies that x1 literally is equal to x2. Another one of these definitions that forces itself to be true vacuously when it is true. That's the horizontal line test, by the way, if you've played with horizontal lines before. Oh, I've got an error. Maybe that's why I was having trouble with Desmos. Y equals e to the x look like that. If I plot a horizontal line like y equals 2, it hits it once. And why is that? There's the places where this line would hit the graph are all the places where an x value gets mapped to 2. And we're saying there's really just one. So yeah, there's only going to be that one spot where a horizontal line crosses that thing. And I wish I could, oh, now I got the slider. Yeah, now you can change the slider around and notice some stuff. When you get to 0, there isn't anything that hits the graph. That is, the line y equals 0 never does touch the graph of e to the x. Any positive number, it hits it, but only once. And For negative numbers, it doesn't hit it at all. Remember, the horizontal line test just says if you intersect the graph, you intersect it once for a horizontal line. Get back to my slides here. Okay, so there's a standard trick that gets used, and it's because this injectivity, being an injective function, is very desirable, and many functions aren't. So the standard trick is to kind of blow off all the things that mess it up. That is, get rid of or eliminate from your domain any x values that cause a multiplicity of inputs going to the same output. And that's called restricting the domain. And let's pop up at Desmos, but I think we want the graph of x squared because it's only F11. I accidentally hit F11 and that sent me to full screen. Didn't know about that. Here's the graph of x to the second power. Clearly the horizontal line test fails. Clearly there's two different x's that go to the same y for a lot of values. To make that not happen, you just want to chop this graph in half. And in Desmos, there's kind of a nice way to do that. If you use curly braces, this will put on a restriction. So for instance, I could say x has got to be greater than or equal to 0 in curly braces, and it makes something now that is one-to-one. This new function, and it is literally a different function because it's got a different domain. The domain is part of what makes the definition of a function. Yeah, this guy is one-to-one, even though it comes from something that was two-to-one. Oh, I already said this. You pick one side. In this case, I picked the positive x values. I could get something that was one-to-one if I picked the negative x values. And you say that's the winner and remove any other inputs that go to that y. So make a different domain. That's what I said before. Oh, cool. I did this all in Desmos, and we saw that the thing after you've restricted the domain passes the horizontal line test. Now, why do we do that? Well, when we're talking about relations, there's this idea of an inverse for a relation, and that holds for functions. In fact, the idea of the inverse probably comes from the function side of things. But when you had a relation, all that we meant by the inverse was just take the pairs that are the pairs from R there, but interchanged with the y in the first slot and the x in the second slot. Yx is in R inverse when xy is in R. That's cool. That's easy, right? You just say, well, if I've got a graph, interchange x and y for everything, and you'll get a graph for its inverse. And that's true for functions as well. You'll hear people say, look, there's a function that doesn't have an inverse, and that's simply false. There is an inverse for it because, well, it's a function, right? And functions are relations, like all squares are rectangles. If you've got a relation, it has an inverse. The real issue is that that inverse might not itself be a function. In fact, often isn't. But if you're injective, that's precisely what you need to guarantee that when you interchange the roles of y and x, you end up with something that is a function. Why is that? Well, the horizontal line test, when the lines are horizontal, and you flip x and y, take the x-axis and make it go where the y-axis was. Literally, I tend to imagine that as a physical motion. Oh, wait, I need to have this on transparent paper. I'd like to be able to show you, here's x. Oh, can I do this? Maybe I can put something on my fingertip. Here's y. What we mean is that, yeah, that the x-axis goes where the y was, and the y-axis ends up where the x was. Yeah, so if you do that, what was a horizontal line becomes a vertical line. So when you say that a function passes HLT, you're also saying that its inverse will pass VLT. In other words, it's a function. I hope that's cool that I'm using the abbreviations HLT and VLT. Everybody knows what I mean. Yeah, cool. All right, so now we're going to finish up by talking about bijections. Basically, bijections are functions that have both of these properties, which is really why we define these two properties. You're surjective and injective. Great, you're a bijection. I want to introduce some terminology that makes this stuff easier to talk about. The first is the image. Oh, see a little flaw in my slide. The part where it's supposed to pause is I wrote the word pause instead of the command. Oops. Anyway, when y is equal to f of x, we say that y is the image of x. That's very standard terminology. So image is the output value. In the same, oh well, yeah, there's a situation where you might have a bunch of functions around. So then if you need to mention what function you're talking about, you'd say y is the image of x under f. In a similar vein, you can say that x is a preimage of y. So a preimage is an input value, an image is an output value. Notice the use of the articles in this. In the one about images, I said y is the image of x. But in the one about preimages, I said x is a preimage of y. Why? Well, in English, the is called the definite article, and a is the indefinite article. We use those when there's a definite thing we're talking about, when really what it's getting at is there's uniqueness. The image, because there's only one image. A preimage, because there may be many preimages. But when you have this injectivity property, preimages become unique. So assuming you've got f is 1 to 1, now you can use the in there. You can say the preimage of y. All right, a function that is both injective and surjective is a bijection. I said that already, but I just wanted to have it on the same slide. Let's think about what these mean in general. Surjective means every y in the codomain has a preimage in the domain. Oh, I guess this is repetitive, but I'm using the image and preimage terminology now. An injective means the preimage is unique. So everybody has a preimage, and it's a unique preimage. What does that get for us? Well, it gets a sort of a perfect matching between the input side and the output side. So let's look at this example in JIAM, starting on page 282. Okay, so this is page 282 in JIAM. The example I want to have us look at is right here. It starts in the middle of the page with that sentence. Let's start by looking at a very simple example. The function involved is 2x minus 1, although you need to be careful at this point now. There's also a statement about what's the domain of the function here. X is a positive integer. You see, the identity of a function is sort of critically tied up with not just what the rule is, but what the domain is. And so if you had 2x minus 1 defined on the real numbers, that's a very different set of ordered pairs than 2x minus 1 defined on the positive integers. By the way, I'll point out I discovered a typo in JIAM while working on these slides for this. So yeah, that you may have a version of the book that has the naturals there, but it's really positive integers for positive naturals, if you like, counting numbers. Well, anyway, this function can't be a surjection, right? Because, I mean, if you're thinking the codomain is the naturals or the integers or something like that, this is only going to output odd numbers. And so it's just not going to work. You won't have an on-to function. But if you create a set, and that's what we're doing here, let O equal 1, 3, 5, 7, etc., then you get a bijection between, well, we're going to show that you get a bijection between the positive integers and this set O. All right, so let's try to follow through the argument that's given here. First, just stating the theorem, the function f from z plus to O, defined by f of x equals 2x minus 1, is a bijection from z plus to O. So we're going to have to do two things. First, show it's a surjection, and then show it's an injection, which is what the first line of our proof says. First, we'll show that f is surjective. What are you doing in that case? Well, basically what you've got to do is pick some arbitrary thing on the output side and find a preimage for it. So that's what we're proceeding to do now. We're considering an arbitrary element y of the set O. That's all we know, that it's in the set O, but that tells you a fair amount. It follows that y is both positive and odd, right? So that means there's an integer k. This is the witness to y being odd, so that y equals 2k plus 1. Also, y is positive because that's what we said. Right? We were talking about positive odd numbers. So from this, it follows, well, I'm just subbing 2k plus 1 in for y in this inequality, right? And then doing a little algebra, and I deduce that k is bigger than negative a half. Okay, but that actually is kind of, that's the wrong thing, because that's not a whole number. K, we know, is a whole number, or indeed an integer. So what's the smallest that y could really be? Excuse me, k could really be? 0. Right? This is a negative number between 0 and minus 1. So minus 1 and anything smaller than that is out, because we're going to be bigger than negative a half. So k is 0 or higher. In other words, k is in that set, the non-negative integers. So then just check that a pre-image for y is k plus 1. What does f do to k plus 1? Remember what f was? It's 2 times a thing minus 1. So we'd have 2 times k plus 1 minus 1, and do the rest of the algebra, and you see that you get y. 2k plus 1 is what you get, but that's what y is, right? Okay, so then the next thing is to show that it's injective. This almost feels like you're not doing enough, but we're doing what needs to be done. You suppose you have 2 different inputs where the function applied to both of them gives you the same result. So that's what it says here. F of x1 is equal to f of x2. And then just using what the function is, 2x minus 1 must be equal to 2x2 minus 1. Then what do? Add 1, and then add 1 and then divide by 2, and you've got that they're equal. So this function 2x minus 1 is a bijection. I didn't do a closing sentence on this one, and I'm not sure. I don't think it's necessary in general, but if I were to add one in, it would say something like, since we've shown that f is both a surjection and a bijection, a surjection and an injection, it follows that it is bijection. I think we should do this slightly more complicated example as well. But I think maybe before jumping into that, let me just point out for you what this function we've just verified as a bijection does. See, bijections pair off their domain with their range, or actually their range is the same as the codomain. The domain and the codomain get paired off in a sort of one-to-one fashion. Each thing in one side is paired with exactly one thing in the other side. So bijections are what we in fact use as the definition for sets having the same cardinality. So we've just shown that the natural numbers, well, the positive integers, and the odd numbers have the same size as sets, which is really surprising if you think about it, because O is missing all of the even numbers, and Z plus has them. Right? So Z plus would appear to be like twice as big as O. It's not, because of the existence of this bijection, which we've just proved is a bijection. You find that these two sets are equal in cardinality. It's a bit of a surprise. That's something we'll see in 2 chapters when we start talking about infinite cardinalities. But this is a little foreshadowing of that. It's true that when you're dealing with infinite cardinalities, your intuition can lead you very far astray. So you might think that O is a smaller set than Z plus, but it's not. And all right, well, this next function we're going to look at does a very similar task. We're going to come up with a bijection that goes from the naturals to the integers. Excuse me. Also, because we'll show it's a bijection. Notice what it does. It's pairing up the naturals, which are generally thought of as a singly infinite list, with the integers, which is thought of as a doubly infinite list. It goes that way for positive numbers and this way through negative numbers. And yet they're in fact equal in size, not as sets, but equal in cardinality. So what's the function do here? It's defined in cases. If you have an even number, you just cut it in half. And if you have an odd number, you do this to it. Uh, you add one, so then that'll be even. Divide by two, that'll be smaller, but then a minus sign. You end up sending the odd numbers to negatives and the even numbers stay in the positives. But, at a high level, what it does is matches the naturals and the integers up in a pairwise perfect matching. Okay, so let's show that it's a surjection. Because that's the two things we're going to do again, surjection and bijection. So, all right, let's see. It suffices to find a preimage for an arbitrary element of Z. Suppose that Y is a particular but arbitrarily chosen integer. There are two cases to consider. It's either negative or it's 0 or higher. Okay, so let's do the 0 or higher first. If Y is greater than or equal to 0, then here's your preimage, twice Y. Why does that work? Well, if X is equal to 2Y, that's obviously even. And so which of these two parts do we use? We would be using the top half. We'd be in this case. And we'd have 2 times Y, and we divide that by 2. Of course, we're going to get Y. So that's what the algebra here is basically running through. All right, well, what if Y is less than 0? Takes a little bit of fiddling with it to figure this out, but that is the number you should use to be a preimage for Y in that case. First of all, even though there's a minus sign on there, as far as even and oddness are concerned, isn't this clearly an odd number? 2Y is even, add 1, that's odd. If it's negative, that doesn't change even or oddness. So it's odd, and that means you're going to be using the second case. Well, look back at here. That's this more complicated formula. So what I have done then is fill in the negative of 1 plus 2Y into the second case, and we're going to run the algebra of that. F of x is f of negative of 1 plus 2y is, oh gosh, that's the formula applied to it. But, you see, it's just algebra from there. It simplifies down to y. So that's a preimage. So those two cases together show you that this is surjective. Now, oh yeah, we've got a summarization sentence here. Since y greater than 0 and y less than or equal to 0 are exhaustive, I think I've got those. Yeah, I've got those inequalities turned around. Anyway, the two cases we looked at are exhaustive. That then every y falls into one or the other of those cases, and so you found a preimage in both cases. Falls at f is surjective. Next, we'll look at injective. Suppose that x1 and x2 are elements of the naturals, and that f of x1 is equal to f of x2. There's actually three cases to deal with. If x1 and x2 are both even, that's one case. If they're both odd, that's another. Or possibly they have opposite parity. Well, if they're both even, then you're going to be using the x over 2 formula, right? So the two formulas give you x1 over 2 and x2 over 2, and those things are going to reduce to saying that x1 is equal to x2. Similarly, when they're both odd, you get the same result. Now, if they have opposite parity, I'm gonna skip that for a sec. If they have opposite parity, where do they end up? The one that is even ends up as a 0 or higher, and the one that is odd ends up negative. So how could those have been equal to each other? We have a mini proof by contradiction there. If you assume they were equal but had their values or their functional values are equal, but they came from things of opposite parity, you get a contradiction because things of opposite parity, one gets sent to a negative number, the other to a non-negative number. Okay, so let's get back to our slides. Well, okay, new topic, really. But it's there to let us sort of even more compactly talk about onto and one-to-one. The idea about images and pre-images, you can expand that to talk about sets, so the image of a set and the pre-image of a set. Um, if you've got a set that's contained in the domain, then this is how you can write it: f of a. So a is a set. It's inside the domain. That is, uh, it is the sort of things that the function can act upon. And so f of a means the set of all things that look like f of an element of a. I'm using little a for the elements of big A. Pre-images of a set are denoted by f inverse of B. And B is going to be some subset of the codomain, right? But I just wanted to point out that this really is a little off because f inverse might not exist, or it might not be a function, but still that's the notation for the inverse image of B. Here's how it's defined. Um, so you've got a B in the codomain, a subset of the codomain. The preimage of B is defined as, well, it's the x such that f of x ends up being in B. So it's the things that get sent into the set B. Why do we have those? Well, mostly just to say this bit about one-to-one and onto in one more way, in terms of these set versions of image and pre-image. So what does surjection means? Um, you're onto if the image of A is B. And your one-to-one, it's a little more complicated, but what it really comes down to is inverse images of sets having one element have to be sets that have one element. Inverse images of a singleton set are indeed singletons. Okay, that brings us to the end of today's slides, and I think that's a good place to stop. We've covered section 6.5 about functions. Next coming up is section 6.6, which is a little compendium of special functions that we will look at. Anyway, have a great rest of your day and hope to see you next time.